Hi, my name is Nina Rands. For those of you that don't know me, I am a committee member, and I have been a committee member since 2013. In fact, the first committee meeting I attended was in Bristol after one of the ACCU conferences. If you ever get a chance to attend a committee meeting, I highly recommend it. It's quite interesting to see how the sausage gets made, I guess. Different parts of the committee work in different groups, and different groups have different dynamics. So it's always interesting to see how which group works. One day I stumbled up upon core, which is what I attend the most at the moment. And core group is the group that looks after the first 15 chapters of the standard, which is the syntax of the language. They were kind enough to let me sprinkle a few comments in the wording, and ever since then I've been known as the comma supervisor of C++. So if you ever find anything wrong with punctuation in the committee, that's come to me. Why am I here? During lockdown, when everyone was learning a new language, I helped a group of very, very clever people write a book. It's a book about modern C++ features, and it's aimed at people who are already familiar with C++, but are not necessarily familiar with everything new that's come in since C++ 11. It focuses on the new features of C++ 11 and 14. Why just 11 and 14 and all of it? Simply because there's so much that putting everything in one book would be just too exhaustive. So we started with 11 and 14, and then hopefully we'll go on to the 17 soon. And I'm really looking forward to it, because that was a lot of fun. We categorized all the features that came in 11 and 14 as safe, conditionally safe, and unsafe based on how easy it is to use them and how easy it is to get them wrong. We also try to describe all the common pitfalls and how you can avoid them. While working on that book, I realized that these days we have quite a lot of terminology in the standard that describes user types with special provisions that the language gives for various different reasons. Sometimes we have certain user-defined types that can use new features of C++, and sometimes it's there because we have undefined behavior, and we want to fix that. Now, when we talk about undefined behavior and compiler making use of undefined behavior, it's not really like compiler goes and finds all the undefined behavior you have and then does something maliciously to trick you. What they really do is they look at your code and then they make assumptions that they can do that the standard allows them, and sometimes those assumptions can break your code if you're not following all the rules. However, for certain common programming patterns, it's so widespread that even if a compiler would ever to make use of that undefined behavior, there would be so much complaint and so much code breakage that they never do. So then we go away and find some sort of weasel wording to put into the standard to make the code that used to be undefined behavior defined for some definition of defined. But before we start, I think it would be good to remind ourselves just a little bit about the C++ object model. And I went ahead and found several sentences from the standard because I can't possibly say it better than the standard can. So this is one of them. The constructs in C++ program create, destroy, refer to, access, and manipulate objects. As you can see, objects are quite basic to any sort of C++ program. And another one is, an object occupies a region of storage in its period of construction throughout its lifetime and in its period of destruction. And here we have quite a lot of things that we're going to be talking about in this talk, which is the storage, the construction and destruction, and a lifetime. We have two other definitions from the standard that I would like to sort of bring up. One of them is the object representation, which is the bytes that the object takes up in memory, roughly. And then we also have the value representation, which is the value of that object. We have different types of objects. We have objects of scalar types or built-in types. All of these are there. Standard null pointer T is the new one that came into C++ 11. And then we have objects of user-defined types. I say class types, but that's because unions are classes too. And then we have arrays of all these things. However, when we talk about objects of user-defined types, there are certain things that normally hold. Normally, we run the constructor when the lifetime starts. Normally, we run the destructor when the lifetime ends. When we copy the values, we tend to use copy assignment and copy constructor. These objects have some layout, but it's not really specified what it is. And the object representation and the value representation that we mentioned earlier tend not to be the same. However, for these things, for these groups of types, some of those things, one or more, do not necessarily hold. So we're going to go through them. And then I'm going to try and mention when each one of these groups matters, when do you want to be careful about it. Some of them you'll probably never care about, and I'll say that too. But if you do find something that might be relevant to something that you use, I kind of hope that you'll go away and find all the details, because I can't cover all the details, and I'm very core-ish, and I like to be very specific, but I can't be as specific as I want to be in an hour and a half. So we're just going to kind of have a run-through demonstration of what they all are. So we'll start with aggregate types, which are types that exist in C++ 98. They're nothing new. When we talk about aggregate types, we talk about initialization. So when we initialize aggregates, we can initialize them as collection of objects. It's called aggregate initialization, and in C++ 11, we got something called the uniform initialization, which is when you initialize things with curly braces, and all of a sudden, all the initializations have the same semantics or similar semantics, which was an excellent idea. Not so excellently executed. But in general, what happens is when you initialize these objects, no constructor is actually run. What we do is we take the initializers that are in these curly braces, and then we initialize each sub-object of an aggregate with the appropriate initializer. So in this case, 1 goes to A, 2 goes to B, letter B goes to C, and 0 goes to L. You don't have to provide initializers for all of them. You can initialize only some of them or none of them. If you don't provide any initializers, then you can either get the default member initializer used, like in the case of C, or if you don't even have a default, then you use empty curly braces. You can also initialize from the object of the same type, and again, you don't get any constructors invoked, you just get member-wise initialization. Not only can we do that, we also have now designated initializers in C++ 20, which means that instead of just writing your initializers, you can name exactly which sub-object you want to initialize. So for example, here I call out that I want to initialize C. This is kind of good because if you keep adding to your aggregates and your initializers are not named, then your initializer may, after a while, change meaning. So if you're playing around with adding and removing aggregate members that you kind of want to use designated initializers, but then again, if you're changing the names, you don't want to, so you choose what you want to do. There are some downsides, well, not downsides, I'm not going to call it downsides, but there is something that you need to be careful of, which is that when you initialize them, the order of initialization is in declaration order, so you kind of have to be careful not to swap around your initializers. For example, in X3, we initialize A with B, but B is not initialized at that point, so both of them have indeterminate values, really. Well, A does, B gets initialized later on. Not only that, you kind of have to be careful of the name lookup. So in X2, the user probably wanted to initialize with the sub-object A, but the A from the outside scope got picked up. Aggregates are kind of interesting because with every new release of C++, the definition changed. There are no 2 releases of C++ that have the same definition of aggregates. And I think it's kind of interesting to sort of see how it evolved, just to see what happens. So I'm going to start with C++ 03, which was the starting one. An aggregate is a class that has no user-declared constructors. All the data members are public. It has no virtual functions, and it has no base classes. And then in C++ 11, we got this. Just to show the difference again. Right. So it looks like we did a lot, although it didn't. The reason we have explicit constructors there and the bracer equal initializers is simply because these are C++11 features. So we needed to kind of include them in the definition. What really changed is from user declared to user provided, kind of, because in C++11 we got the ability to default and delete special member functions. And deleted and defaulted special member functions are user declared, and we allow them in aggregate, so now it changed from user declared to the user provided. The no bracer equal initializers is kind of sucky, because you have an aggregate like this, and you write all your initialization, excellent, no constructors get invoked, and then you want to add a default member initializer, and everything breaks all of a sudden for really no good reason. So that's the first thing that we fixed. In C++14, we removed the requirement on bracer equal initializers, and now you can have those two, and it's still an aggregate, and you can still not write constructors if you don't want them. In C++17, what we did is added base classes. It's the last one. So you still have to have only public base classes. There's a mention of inherited constructors, but again, inherited constructors are a new feature of C++17, so we didn't actually restrict anything, we're just taking into account those. The question now comes, how do we initialize base classes? Well, we initialize base classes and all of its non-static data members first in the order of declaration, and then we go to the non-static data members of the most derived class. So here's an example. When I initialize my x1, I first initialize the base class y and its member, and then initialize the non-static data members of x. There's something called the brace elision, so you don't actually have to put the braces around the initializers of base classes. It saves you some keystrokes. May get you some hate from people that are going to be maintaining your code, but you do you. Right, so that's C++17. Moving on to C++20, you'll notice the difference in the top row. So we went from user provided to user declared. Now, if you remember, we had user declared in C++03. We changed that. So why are we going back? Turns out we made a bit of a mistake. So this is an aggregate in C++17. However, it's a class that the author didn't want default created, so they deleted the default constructor. There might be some other things in the class, but the point is this class is, by chance, an aggregate. So if you try and do just a declaration that would invoke a default constructor, the compiler goes away, finds a default constructor, sees that it's deleted, and says, no, you can't do this. But then you go away and you put curly braces because we told you that you should do that. It's uniform initialization. Put curly braces everywhere. So you do. And all of a sudden, it can be initialized, and you don't see that. But now that we fixed it in C++20, you get a compiler error again. Similarly, if you have a class where the value initialization is deliberately disabled by deleting a constructor like this, again, if you try and initialize it with just a number, it would be ill-formed because the value constructor is deleted. And if you try to put, like even if I had more members and I put more numbers, the constructor would not be found. But if I put curly braces, it all works. Probably not what the user wanted. So again, in C++20, we fixed that. There's a paper, P1008, if anyone wants to see more details on what exactly happened. Now, when I wrote this, I thought, damn, we have C++23 right now in draft, soon to be released. And I'm going to have to change my talk and say the definition stayed the same. But it actually changed. It changed in C++23. See if you can spot the difference. I have copy-pasted this from the standard. Nothing changed, we just reformatted it. So we moved the virtual base classes and virtual functions into the last one and then put private and protected at the top. I don't know who did this and why they did it, but it amused me. So aggregates are really one of those things that are different in every release of C++. There is a trait It's an is-aggregate trait. It tells you whether a type is an aggregate or not. It was introduced to resolve a specific problem in library where we had emplaced and construct idioms that would take arguments and then fast forward them to the type. Perfect forward them to the type. The thing is, if you try to use what are they called? Not the curly braces, but parentheses. Thank you, Roger. If you try to use parentheses, then you can't really initialize an aggregate because aggregates don't have constructors and can't be initialized using parentheses in C++17. However, if you use curly braces, then you get a different overload resolution on your constructors because the uniform initialization is excellent. So what you end up doing is you kind of have to branch on whether your class is an aggregate or not. So you write a specialization for an aggregate and then you initialize using curly braces. And if it's not an aggregate, you initialize using parentheses and everything works. This is pretty much the only case I found for an is-aggregate type trait. I'm not familiar with any other use cases. However, somebody said, yeah, why don't we just fix that? Why don't we allow aggregates to be initialized using parents initialization? And that's exactly what happened in C++20 with P0960. We got the parents initialization of an aggregate. However, it tries to mimic the parents initialization of a non-aggregate. You still don't get any constructors invoked. It's still member-wise initialization, but it has slightly different semantics. So whenever you use uniform initialization, you can't get narrowing conversions. This is kind of supposed to be a safety thing. So you do get narrowing conversions when you use parentheses, which you may want to be careful of. You can't use designators, you can't get brace elision, and the temporary objects have slightly different lifetime extension rules. So you also might want to be careful about that. However, now that we have parents initialization using for aggregates, I'm not really sure whether library trait is still necessary or whether you can, I don't know. Good question. Right, moving on to standard layout types. Standard layout types have awesome name because the thing about them is that their layout is standard. It doesn't mean that the standard defines what the layout is, it just means that the layout across different implementations is standard, and not just across different implementations, but also different certain programming languages. C. So what are these standard layout classes? They have the same access control for all non-static data members. This is because when you go into the standard, when we talk about layout of non-static data members, we only really ever talk about a little bit when it comes to the same access control, but we don't say anything about what happens across different access control classes. If it has non-static data members, it has them declared in one base class in the whole base class hierarchy. This is a slightly more complex way of saying it. I have a slide that's kind of hopefully going to demonstrate what that means. So A is empty, B has one character. C, they're both standard layout, obviously. C is a standard layout because the base class is empty, so the only non-static data members exist in C. D is empty, A, base class is empty, and the only non-static data members are in B. There is an issue with E. E is not a standard layout because it has non-static data members in one of the base classes, and then again E. And I think G is the only one that's still interesting. So even though A is an empty base class, it still counts as a non-static data member of G. And then we also have some non-static data members in B, so this is not a standard layout. By the way, I brought some things here because every time I go through these slides, I always find typos. And I hate typos. So I thought, if anyone spots any typos here, I have a non-healthy reward and a healthy reward. Did you find a typo?
Yeah, every your previous slide had 2 F's in.
Do you want a healthy or non-healthy?
I shall donate.
You shall donate, okay.
I'm already on the non-healthy.
Excellent. I'll keep it if anyone heckles to throw at them. But thank you, I'll check that. So yeah, that's about the base classes non-static data members. There is something that's slightly relevant to that, which is that no base classes need to require a distinct address. which is an interesting rule. The question is, when are types required to have distinct address? Now, normally, two objects have to have distinct address, obviously, but there are some exceptions. One of them is for when one object is a sub-object of another one, and so it's really first non-static data member, or it's an empty base class. In those cases, those objects may share the same address. We did change the rules a little bit in C++20, so it went from base class of 0 size to any sub-object of 0 size, and you might ask yourself, how can we have a non-static data member of 0 size? Well, we can with this new attribute, no unique address. So if you have an empty class that is a non-static data member and you put this attribute, if your compiler supports it, then that non-static data member might not take up any space in your class. But that's not really what's important. The important thing is different types. Two objects of the same type can never have the same address. So really what we're talking about here is same types. Same types somewhere in the base class hierarchy and possibly the first non-static data member. So A, B, and C are all standard layout because they have no same members anywhere, no same types in the class hierarchy, while D has an A in B and in C, so these two need to have distinct address. And in E, I have my base class in B and one of the non-static data members of the same type, and those two can't share the same address. Therefore, the base class needs to have a distinct address. Has no virtual functions and no virtual base classes. This is really because we don't want to have any virtual function pointers. Virtual tables, sorry. And we can't have any reference members, mostly because we don't talk about the representation of reference members, and all the base classes and all the non-static data members have to follow all of these rules. What can we do with it? If you remember when I was talking about addresses, because of the rules that we have for the non-standard layout types, it means that all of your base classes and your outside object and your first non-static data member all share the same address, and you can convert your pointers between those. You can also use offset off to get to things within your class in a well-defined manner. You can actually get offset off with non-standard layout types for certain cases, in certain compilers, but that's probably not going to be portable. Another interesting thing about standard layout types is that you can use this really cool trick with unions and standard layout types. And to do that, we have a notion of something that's called common initial sequence. So if you defined your non-static data members in two standard layout types, and if in the declaration order the types match, then they make up the common initial sequence. That makes sense? In C++20, we also have the no unique address. So if one of them has a no unique address, the other one has to have it too. So now that we have two standard layout types and they share a common initial sequence, what we can do is we can put it in a union. And then if one of them is active, we can read the common initial sequence through the inactive one in a well-defined way. It has to come from a union. You can't have pointers and references bound to the inactive member and then read it. But if you read it through a union, it's all fine. So this is an example. I have two structures. They share a common initial sequence in the integer, and then I put them in a union. I create the union object. I initialize the A to be the active member. And then if I try to read the integer from B through B, that's fine. But if I try to read the character, it isn't. Looks a bit silly like this, so I'm going to give it better names. Now it might make sense. So if you're having standard layout types that you use in the union, you can keep track of which one is active by having type information in your common initial sequence. The read does need to happen, like I said, through the union. So if I bind a reference, it's undefined, which really means if you're doing these reads in functions, you really have to be passing in union objects rather than members of the union. in order to have this well defined. We do have a trait. You would probably use this trait if you're doing any of these union trickery or offset off or, I don't know, pointer into convertibility, and you want to make sure that your code is fine, so you would static assert on it, but you can't really use it in any sort of clever way like you could is aggregate. I kind of played with it. Oh, you have a...
Just to clarify, at no point did you mention access control, so standard layout has nothing to do with private or public, correct?
No, it doesn't. It doesn't. So everything needs to be public. Oh, sorry. Everything needs to be the same access control. So yeah, you can have private members provided they're all private. Why do you mention that?
No, just clarifying.
Yeah. No, nothing along those lines. Yes. The standard layout really is... What you would use standard layout is, if you want to use offset off, if you want to convert your pointers between the base classes and the object and the first non-static data member, and if you're using this union trickery. It has nothing to do with access now. I played around with this is standard layout when we were writing the book, and then when I was writing this talk, and I found quite a lot of quite spurious mistakes. So I would assume that it's not actually widely used because compilers tend to fix things if they need to be fixed. So I'm just going to assume not a lot of people use it. Right, moving on to trivially copyable types. Thank you, Alistair. So we have a lot of trivial words in the standard, and sometimes people might get confused just because the sheer number of terminology. So we're going to cover the trivial special member functions first because we will need them later on in the definition of both trivial copyability and trivial types. So trivial default constructors is a constructor that's really pretty much a no-op. And such a constructor is not user provided, meaning user didn't want anything special done for this type. There are no virtual tables to initialize. The same applies for all the base classes and all the non-static data members, so they also have trivial default constructors. And then there are no default member initializers because absolutely no initialization needs to happen for this type. We also have a trivial copy constructor and assignment operator. These are the rules. Again, it's not user provided. There are no virtual tables to worry about, and all the base classes and non-static data members also have the corresponding copy constructor assignment operator to be trivial. So everything that you would invoke as a part of invocation of this special member function is also trivial. And finally, we have a trivial destructor. Again, not user provided, not virtual, and everything that it might invoke, if it were to invoke, would be trivial. So again, this is very much a no-op. So now we come to the definition of a trivially copyable type. A trivially copyable type is a type that's firstly copyable. It has to have at least one non-deleted copy operation. Doesn't matter which copy operation, as long as it has one, it's copyable. In C++20, we also have concepts. So when we talk about these copy operations in C++20, we say eligible, and eligible just means non-deleted and its constraints have been satisfied. And a few other things, but okay. If it has copy operations, all of those need to be trivial. And it has a trivial non-deleted destructor. Alistair, would you like to ask a question?
No.
There are no requirements on access control or ambiguity of a call. So as long as all of them are trivial, whether they're actually public, whether if you were to invoke them, it would be an ambiguous call, or perhaps even that specific copy operation is deleted, we don't talk about that. This is a trivially copyable type, and there's a reason for it. So what are the implications? Because we don't have anything that we need to do when you copy it, the value is actually contained in the underlying object representation, right? There's nothing special that we need to do. And because the value is contained in the underlying object representation, we can take that object representation and then bitwise copy it into another object of the same type and have the resulting type have the same value. We can also do this into an array of char, unsigned char, and STD byte because these things are object representation in C++. And not only can we do it, the compiler can do it. That's another hint. So we have a trait, is trivially copyable. It's been introduced in C++11. If you want to do any bitwise copy of your types, you should check whether your type is trivially copyable before you do that bitwise copy, because if it isn't, then you have undefined behavior. But like I said, it doesn't actually check whether that particular copy operation that you're doing is possible for some definition of possible. The reason it doesn't do that is because, like I said, compilers do these copying around too. And when the compiler comes across a trivially copyable type that has some sort of copy operation invoked, it has already checked the semantics of that copy. So it doesn't have to do any sort of semantic check. It can just implement it as a mem copy. However, when you write bitwise copying instead of invoking copy assignments and copy constructors, you better make sure that that copy can actually be done. So as an example, I have here a structure X, and that structure is only move constructible. It is not copy constructible by design, for whatever reason. Now, that structure is actually trivially copyable. And I can possibly implement a copy, which is completely well-defined, where I pass in this X, my copy checks whether it's trivially copyable, so it doesn't do anything silly, and it does the mem copy, and it's all well-defined. The problem is it does a normal copy operation, doesn't do move construction, does copy construction, which the author of X didn't want to do. So if you're writing this, somewhere in that call stack, there better be a check on whether X can be assigned to or copy constructed from a constant L value reference. That's all trivially copyable types. Now on to trivial types. Trivial types are trivially copyable types that are also trivially constructible. That's it. You can't do anything with them. There's no special provisions that you get for trivial types. They're kind of a little bit of a remnant from the days when we had plain old data types, and plain old data types were trivial types. So we have a definition because there are still things in the library that need to be trivial. But if you yourself write a trivial type, that type doesn't get any special properties. So if you have, there's a type trait too. If you're using your type trait is trivial somewhere in the code, it's quite likely that you wanted something else with trivial in its name. Unless you're checking for these types in the standard library that are said to be trivial, it's probably not what you want. So, beware. It's one of those things that you can ignore, probably. Next are plain old data types, my favorite. I say that because we spent probably 2 months looking into the reasoning about plain old data types. They came into C++98 as a way of defining which types have the compatibility with C. And these are the types that look like C types and behave like C types in certain situations, meaning construction, destruction, and copying. And even if you look into the definition of a plain old data, the original definition, you might recognize things there that we discussed in standard layout types and in trivially copyable types. We have the no user declared constructors, no user defined copy assignment, no user defined destructor. Then we have these no private or protected non-static data members, base classes, virtual functions. It's pretty much all the same. And not only that, people realize that you can use standard layout types in a way that gives them the benefits of a standard layout type without necessarily requiring those to be trivially copyable. And similarly, you can use the trivially copyable benefits without necessarily requiring those type to be standard layout. So we just split the two, and we got the definition of a standard layout type and a definition of a trivial type, and then the whole definition of plain old data was no longer necessary. Now, this is why we have trivial types. for the sole purpose of covering the whole of this definition. But what we really need is either trivially constructible types in cases where the construction needs to be trivial, which we'll come to later, or we need trivially copyable types in order to do the bitwise copy, but we don't really need trivial types in their own. Anyway, when it comes to plain old data, we deprecated the term and then removed it in C++20, which really means that we went through the standard, found all instances of POD, and replaced it with trivial standard layout. That's all. There was also a library trait, is-pod, which was introduced in C++11 and then deprecated in C++20. I'm doing this quite fast. Right, coming to literal types. With C++11, we started moving quite a lot of functionality into compile time, with a view of doing slightly more complex things at compile time, with possibly even basing some sort of a reflection facility on the compile time stuff. And with that, we got an ability to create user-defined types at compile time. And those types that we can create at compile time, we're giving the name of literal type. So, a literal type is one that you can possibly create at compile time. It doesn't mean that every instance of a literal type can be created at compile time. It just means that there is an instance that you can create. For some initialization expression, it may be created at compile time. And not only that, it doesn't really mean that you can use this object at compile time. We don't talk about that. It's really a creation. Its literal type definition is something that if you ever come across things that you need to create in compile time, it's good to go and check what you need to satisfy. But really the definition in itself isn't particularly useful, and you'll see why. So when we talk about compile time in the standard, we never really say compile time. What we say is constant expression. And not only constant expression, it gets even more convoluted. So everything that you do at compile time needs to be triggered by some sort of constant initialization. And constant initialization needs to be done using constant expression. So constant expression is really a thing that can be calculated at compile time. And with that idea of a constant expression, we also got a few new keywords so we can make use of this. We got const_expr, which is a keyword you can put both on variables and functions. Your const_expr variables are constant initialized, meaning they get initialized at compile time. They're also const implicitly, and they have constant destruction. Your const_expr functions, on the other hand, are functions that can, for some arguments, be invoked at compile time, but not necessarily for all arguments. And also you can execute them at compile time or at runtime just fine. Unlike const_expr functions, const_level functions can only be executed at compile time, and they don't exist at runtime at all. And then we also have this new const_init, which is applied to variables, and unlike const_expr variables, const_init ones are not actually const, and they don't have constant destruction. I'm not going to go into the details of all these keywords because the whole constant expression stuff in the standard can probably have a talk of its own. But I am going to point you to a few things. David, who was involved in a lot of these things, has done a very good talk about what it is that we have when we talk about constant expressions. And it's really two sets of things. You have things that will never be possible at compile time, simply put because those resources might not be available at compile time, or that information might not be available at compile time. But there are also things that are very difficult to implement. And it's because compile time evaluation is different to runtime execution. You don't have the benefits of an optimizers and things like that, so it can be quite exponentially complex even for certain things that you might assume to be simple. And Andrew Sutton wrote a very good paper to give you a mental model when it comes to thinking about compile time metaprogramming. However, we are still expanding, and with every new release of C++, there's more and more things that you can do at compile time. What are literal types? The scalar types reference is referring to literal types, array of literal types, void, out of all things. And that's a bit of an interesting story. It only came in C++ 14. And the reason it's there is when we defined const expr functions, we said const expr functions need to return literal types. Why? If we execute them at compile time, that everything that they return must be creatable at compile time, therefore they need to return literal types. Excellent. And then we released it. And then people went to their code base and they applied const expr wherever they could. And for some of those cases it worked, and for some of those cases it didn't work, but for no good reason. They had functions that were in and of themselves possible to execute at const expr. They just took parts of the code and put them in a function that they just invoke for making the code look simpler. But that function itself was returning void, and then because it was returning void, all of a sudden it didn't return a literal type, and that could not be done at compile time, so the whole thing couldn't be at const expr. So to fix it, we added void as a literal type, as a special provision. And then there's also the literal class type, which is what we really care about, kinda. So this is the original definition in C++ 11. It's a type that has at least one way it can be constructed with a constant expression. So it has to have a const expr constructor that is not a copy or a move constructor. I mean, you don't have to create one and then copy move it. It can just be created in a constant expression. And then if you do have any brace or equal initializers, they also need to be constant expressions. And all the non-static data members and base classes have to follow the same rules, and your constructor needs to be trivial. You may ask yourself why. Because when we talk about const expr variables, they need to have constant destruction too. And a trivial destructor is const expr pretty much. We kind of changed it in 17 to add lambdas. So lambdas are now literal classes, and you can have lambdas at compile time too. And in C++ 20, we simplified the definition. We changed the trivial destructor to become const expr destructor because we have added the ability of adding things into the destructor and still keeping a constant expression. And we also removed the requirements on brace or equal initializers. And the reason for that is, when you talk about constant initialization, what you really need is the whole expression to be constant. We talk about literal classes and literal types, but it's really what's involved in that initialization, that specific initialization, that needs to be constant expression. So having a requirement that all brace or equal initializers are constant expressions, if you don't actually use brace or equal initializers in your constant initialization, is unnecessary. And I would argue quite a lot of other definition is completely unnecessary. Now, we have a library trait, is literal type, which was introduced in C++ 11, deprecated in C++ 17, and then removed in C++ 20, which tells you something. And that's that this is not a particularly useful definition, because, like I said, this is not about whether a type or a class is a literal type or class, whether it follows all these rules. It's whether this specific initialization can be done at compile time. And in fact, when you look into the rules of constant initialization, everything that gets invoked as part of this initialization needs to be const expr. So we actually cover all of this by checking whether that initialization is constant expression. And this is pretty much what I'm talking about. So I have a structure here which has a const expr constructor, 1, and one which isn't. So if I try to create a constant init variable, which is default initialized, it's fine, but I can't initialize it with an integer. It gives me an error. The curious thing that we still have as a requirement is that we need to have a const expr destructor, despite the fact that the const init variable is not required to have constant destruction. So, I actually tried removing const expr making this constructor not const expr and then doing const init, which kind of goes against what the definition of literal type is, and all compilers allowed me to do that. So I expect at some point we're going to get rid of the definition of literal type and just sort of subsume all of that into the definition of a constant initialization. So yeah, literal type is something that you really don't have to worry about. It just kind of gives you ideas of what you can or cannot have in your class if you want to use it at compile time. Moving on to structural types. Everyone still awake? Structural types are also relevant to compile time. Now that we have the ability to create objects at compile time, the question is, why can't we have them as non-type template parameters? I mean, we can't create them, so what's the problem? The problem isn't just creating things at compile time. The problem is also checking for equivalence, but not just checking for equivalence of two objects, it's checking for the equivalence of instantiation. And the way this normally happens is the value of your non-type template parameter is mangled in the instantiation. And that's how the compilers check whether two instantiations match. So there was an idea of having types that have equality operator or spaceship operator used as non-type template parameters. But like I said, the problem isn't whether they're equal, it's also what their value is and how can I represent that value in my mangling. So people thought about whether they would just disable non-type template parameters or do some sort of limited scope or what can be a non-type template parameters, and they went for the latter. Like, start with something, and then as we learn about this, we're going to figure out a better way of doing it. And the current subset are class types that are literal class types, obviously, so they could be created at compile time, and for which all base classes and non-static data members are public, non-mutable, and of structural type. What compiler really does is mangle the value of all your public members into the instantiation with the assumption that the value is not necessarily the value of all the non-static data members, but at least that. And then I think the idea is that we might provide some sort of a special operator that returns a normalized value that can be used at some later point, but I don't think we've done much with those proposals at the moment. And this is what it looks like. I'm not sure if you can see that. But I have a structure X, which is a structural type, meaning it can be created at compile time, and it has only public members, and then I can use it as a non-type template parameter. And there you see that GCC mangles the value of all the non-static data members in the name of the instantiation. Clang does pretty much the same thing. There's no type trait for structural types, pretty much because you don't need it. I mean, if you can't use something as a structural type, you'll know at compile time. And finally, we come to implicit lifetime types. When talking about implicit lifetime types, we do need to talk about when does an object start its lifetime. And the standard is very clear on that. There are only certain things that start an object lifetime. It's a definition, it's a new expression, creating a temporary object and changing a union. Again, direct quote. And then you have something like this, which is a very common programming pattern. You allocate some bytes, you point a pointer to it, and then you initialize your sub-objects and you return the pointer. Unfortunately, this is undefined behavior. And the reason that's undefined behavior is because we didn't actually start the lifetime of either X or its sub-objects. Now, this is one of those things when I said, you have undefined behavior, but no compiler is actually going to break this, because if they do, I mean, who's going to use that compiler, right? There's another case. Now this time I'm not going to access my sub-objects. All I'm going to do is allocate the memory, and then I'm going to calculate where the end pointer is. And then I go into the standard and take a look at when can I do pointer arithmetics, and it turns out that I can only do pointer arithmetics on an array, and I don't have any arrays. There's no arrays in my code. That's undefined behavior. That's STD vector. Meaning, again, a very common container has in its implementation undefined behavior. No one's going to break this, right? Why would they? They would break STD vector. So we said, well, let's put some weasel wording into the standard to make this well-defined. And we thought about when does it make sense to make this well-defined? And the outcome was, well, if the types have trivial constructor and trivial destructor, then they can probably just come into existence when they need to come into existence. So we decided these are the types that have this special provision given to them. It's scalar types, array types, and like I said, aggregate classes because, like we said, they get initialized without a constructor, and classes with a trivial, at least one trivial constructor and a trivial destructor. And then we went into the object lifetime definition, and we sort of squeezed this new thing, an operation that implicitly creates objects. We went and defined what those operations that implicitly create objects are, which are these. And then we also fixed it for arrays to say whenever you start a lifetime of an array, you also implicitly create objects within the region of that array. Now, the way this works is a little bit wishy-washy. So what we do is whenever there's an undefined behavior, well, whenever there's an operation that says for this operation to be well-defined, you need to have objects of these types. If objects of those types are implicitly, implicit lifetime types, brain fog. If those objects are implicit lifetime types, and this is an operation that implicitly creates objects, then you get an object. And the type that you get is the type that would make that code well-defined. Now, that doesn't mean that you can implicitly create an integer for the code that presumes this to be an integer to be well-defined, and then later on use it as a character, and then presume that all of a sudden you get some sort of special implicitly created character. No, once you kind of bake in a type, that's the type it has, unless it's also an unsigned char, which is an object representation. But really, once you implicitly create a type, that's the type that's presumed to exist there. And then you get well-defined behavior. So now that we have that previous example, what really happens is when we dereference P, that's only well-defined if a structure of type X exists there, so X pops into existence. And then we can only assign to A if A has started its lifetime, so A pops into existence. The same happens to B, and now this is well-defined. Similarly here, the only way that arithmetic would be well-defined if there's an array of characters, and in order to do that, an array of characters magically springs into existence, and this is well-defined. When I gave this talk at CPPCon, there was no implicit lifetime trait. But since then, we got it. So now you have a way of checking whether your code that does this thing is actually valid. And you do want to do that because quite often you would inherit that code from some old code bases rather than write new ones, but you can still get into a situation where you expand your already existing types so they stop being implicit lifetime, and then all these assumptions stop being valid. We also have a start lifetime as facility in C++23, which, like I said, is currently being balloted, so we should, I think, release it in the summer. Which helps you do this funky dance of aligning memory and then reinterpreting it and all that. So you give it a memory and then you get back a pointer to a type that has already started its lifetime. There's a very good talk by Robert Leahy where he goes into how start lifetime as is implemented and how they use this whole implicit lifetime and the new facility. And it's a very interesting talk. It's almost like an American documentary. It's full of suspense. So if you have a moment, I highly recommend you take a look at that talk. Ooh, I was fast. No, too much coffee. Right, so this is a bit of a summary. These are the types that we have. The aggregate types are relevant to you when you want to initialize something. The good thing about them is you don't have to write all the constructors ever to initialize all the possible combinations of your non-static data members. You just initialize them using curly braces and it all works fine. You have trivially copyable type. You care about those when you want to do some sort of bitwise copying. And you do want to check for the is trivially copyable before you do that bitwise copy, or you might have undefined behavior. And not only that, you also want to check for whatever copy operation you're doing to be valid for the type you're doing it with. You have trivial types, which nothing. They're a remnant from the old days. If you have anything that's doing is trivial, I highly recommend you check whether that's exactly the right kind of trivial trait that you want to be checking for. You have standard layout types, which you can use when you want to get pointer interconvertibility, when you want to do the funky union access to read different parts of union objects in order to determine what exists in that union, or you can use std variant, which gives you that for free. You have POD types, which are currently only used for certain library requirements, but you can't really do anything special on your own with those. You have literal types, which are a rough requirement for constant initialization, but you almost never need to know about them. You just need to make sure that your initialization really is constant, and if it isn't, you will find out at compile time. Chocolate. Where in?
Initialization for literal type.
Oh, God damn it.
I donate my treats to Roger in order to curry favour with an agency that committee BSI.
Rogers also sits in court, so he might. We had a play, I think, once in committee about who's going to be able to get a certain word into the standard. So we now have vivisection somewhere in the standard in one of the examples. Yes, we take our work very seriously. Anyway, for structural type, illustrative type, yes, right, next one, structural type. Structural type is the type that you can use as a non-type template parameter. At the moment, it's quite limited, but we are looking to expand what you can put there. There's no trait, because what would that trait even do? And then finally, you have implicit lifetime types, where you can do this magic of objects just spring into existence if they need to spring into existence. And for that, we have an is implicit lifetime trait and a very useful start lifetime as facility. And that's all.